This video is about specific heat capacity and is one of the required practicals for your GCSE. In this video I'm going to be using one of the virtual physics laboratory simulations that Dr. John Nunn has kindly given me permission to use in these videos. This one is the specific heat capacity 2 simulation. First things first, we need to define specific heat capacity. Specific heat capacity is defined as the amount of heat that is transferred to change the temperature of 1 kilogram of a substance by 1 degree Celsius, which is the same as 1 Kelvin. So the units are joules per kilogram degree Celsius or per kilogram Kelvin. If I take the same mass of two different substances and I wish to increase their temperature by the same amount, it will take different amounts of energy and therefore different amounts of heat transfer to do that. Now, one of your required practicals or core practicals is to measure the specific heat capacity of a substance, and it may be a solid or it may be a liquid, and it's the same approach for both. So I will show you measuring the specific heat capacity for a solid. Here I have the solid. It is a copper cylinder, and inside this copper cylinder has been inserted a heater and a thermometer, and usually you would use some heat transfer medium like Vaseline or petroleum jelly to transfer the heat from the heater into the copper. If we didn't have that, there'd be an air gap, and air is a very good insulator of heat, so that would reduce the rate that I could transfer heat into the copper. The whole of this apparatus is surrounded by a layer of insulation, and that is there to reduce the amount of heat that radiates from our copper. If we leave this experiment long enough, eventually the rate at which I put heat in will be equal to the rate that heat is leaking out. That is, the radiative heat out will be at the same rate as the heating that I'm putting in. Remember that heat is a store of energy. We are using an electrical heater, and we will measure the amount of heat energy that we are putting into this copper block by measuring the power of the heater and timing how long the heater is turned on for. Electrical power is equal to the potential difference across the heater multiplied by the current through it. Power is defined at the rate of doing work. In other words, the amount of energy that I transfer divided by how long it takes to transfer that energy. And combining these two equations gives us an equation for the work done by the heater. The potential difference across the heater multiplied by the current through the heater and multiplied for the amount of time the heater has been turned on for, that will be equal to the amount of energy that we've put into that heater. And that amount of energy will be the heat that we've put into the heater. And so we can rewrite our first equation for specific heat capacity like this. You'll notice that I've included a delta, the Greek letter delta. The delta indicates a change, and it's because as this experiment runs, the longer that the experiment is running for, the hotter the copper block will get. So the variables that I'm changing is the time that the heater has been turned on for as my independent variable, and the temperature that the heated block arrives at as the dependent variable. Everything else here will be control variables. Whilst I could change the mass of the block, I'm going to choose not to. Whilst I could change the potential difference across the power supply, I'm going to choose not to. Whilst I could choose to change the current through that heater, I'm going to choose not to. And the material that I use, again, I could choose to change that. I'm choosing not to. And so those are my control variables. I'm going to perform an experiment to measure the specific heat capacity of copper. So here's our experimental setup. What we've got here is a copper block here on the left with the heater into it. And you can see in series with this heater is an ammeter. That ammeter is going to measure the current passing through the heater. That's why it must be in series. We can see that in parallel with the power supply, and therefore in parallel with the heater, is this voltmeter. And so that will be measuring the potential difference across them. And when I turn this heater on, the timer, which is the stopwatch, will automatically start. I'm making sure I've got insulation, and now I can start recording my data. what this simulation will do is automatically plot my graph for me, which is quite helpful. So all I have to do is click the plot button and it will automatically plot a point for me. So here we go. Let's turn it on and let's press record data. And we can see the graph shows a very gradual curve initially. The reason why we have that gradual curve initially is because it takes some time for the heat to conduct from the heater to where the thermometer is. Now this part of the graph looks much straighter. We expect to see something like a straight line. That's what we would expect the results to show. And we'll keep gathering results for quite some time. I may speed this part of the video up. Now you may notice that the line appears to be starting to level off. The gradient of the curve is reducing, and if I leave this running for long enough and storing this data for long enough, then indeed eventually that line will become horizontal, zero gradient. The reason for that, as I've said, is because the temperature will not be increasing. The temperature will not be increasing because we'll be putting energy in at the same rate that energy is radiating out due to this radiative heating. We will be radiating heat as all bodies do. So now I want to use this graph. I'm going to find the gradient of this graph. Unfortunately, the line is a bit thick, so this is going to be quite difficult to do accurately. But let's take this point down here where the line starts appearing to be a straight line. And if I take those 2 points, let's move this one to the left slightly. If I take those 2 points, I can see on the x-axis where we have time, that's at 10 seconds. And the y-axis where I have temperature is between 20 and 25 degrees Celsius. In fact, I think that's exactly halfway. So I'm going to call that 22.5. Now I'm choosing to use this point. There's 2 reasons. The first is that it appears as though the gradient of the graph is reducing slightly after this point. And the second reason, from a practical point of view, is it's going to be easier for me to interpolate between these 2 grid lines if it is pretty much halfway between them. And so I've chosen that point. I don't have a huge range of temperatures, and if I was doing this in a lab, I would leave this running for much longer to get a larger range of temperatures. The larger the range of temperatures, the smaller the uncertainty in my answer. My range of temperatures is 20 degrees Celsius, and my time interval is 40.0 seconds. Let's write down what we know then. The mass of the copper block was 2.50 kilograms. That's what it said on the simulation. Our change in temperature is equal to 20 degrees Celsius. And our interval of time is equal to 40.0 seconds. While the simulation was running, you can see that we had a very stable current of 10 amperes and we had a potential difference of 30 volts. So I can write those down as well. Now all I have to do is plug these data into my equation. Specific heat capacity will be 30 multiplied by 10 multiplied by 40 divided by 2.5 and divided by 20 degrees Celsius. And that gives us 240 joules per kilogram per degree Celsius. That seems a little bit low to me. Well, I think it should be nearer to 390, maybe 385 or something. So I'm not convinced this has given me the right answers. So let's just run this in slow motion again and look what happens to the results. Remember, I only ran it for about a minute. So this time let's run it for much, much longer. So you can see the graph is looking far more curved than it did last time because we've allowed it to run for much longer. And the gradient is reducing. So what does that mean for the specific heat capacity? And can we explain this using physics? been running for about 3 minutes now, and you can see that the latter part of the line is looking still a bit curved but more straight than that initial part of the line, and the gradient is clearly more shallow than it was before. So we used the wrong part of the line, didn't we? Now if the gradient is less steep, the gradient of this line is the change in temperature divided by the change in time. In other words, it is the delta big T divided by the delta little t. So if you look at the equation I've written above here, I could rewrite this as V times I divided by M, and all of that is multiplied by 1 divided by the gradient of this line. And you can see there that the parts I highlight are equivalent. That little t, delta little t divided by delta big T is 1 over the gradient. And that dot just means I've multiplied those together. And so if the line is less steep, so the gradient goes down, the specific heat capacity will go up. And that's what I predict, because I think this number here is too low. So I left the simulation running for a little more than a minute and took a data point, and now I'm going to run it a little bit longer and take another data point. And we're going to see if we can do get a more accurate answer after leaving it running for a little while. So I've left it running for a minute, and now I'm going to take a screenshot. It probably won't be exactly a minute, well, not quite, but it's close enough. So there's my first data point. Now let's collect the second data point. So now it's been running for around about 2 minutes longer, so it's nearly up to 3 minutes. Let's take a screenshot, almost exactly on 3 minutes, and I'm going to use that as my second data point. So let's pop this in here. Now you can see from the stopwatches that the first one I stopped at just a little bit shy of 1 minute, the next one I stopped at just a little bit shy of 3 minutes. So I'm going to call that time 120 seconds. Now I don't think there's any value to me giving it to more precision than that. The difference in temperature, we've got a temperature of 81.2 from a temperature of 44.3. And you can see to 3 significant figures, 36.9. If I'd given my time to more significant figures, it would have only been on the 4th significant figure that we'd see a difference. And there's not much point when my current and my, actually I am given them to 4 significant figures, but my mass is only given to 3 significant figures, and my temperature is only given to 3 significant figures. So there's no advantage to giving the time to more than 3 significant figures. So when I substitute those numbers in, I get 390 joules per kilogram degrees Celsius, which is much closer to what I thought it should be. In fact, if we just go back to our simulation and type 390 and press check, it says, well done, yes, I got it right. So the initial mistake we made was we used the early part of the graph. When you conduct this practical, that's something you need to be careful of. Leave it for a little while to make sure the heat conducts to the thermometer and you have that constant rate of heating, and then you're going to get a straighter line, and you want to use the straight part of the graph to calculate or from which to extract the results to calculate this, this specific heat capacity. So there's our equation in full again, just as a reminder, and that is everything I need to say about measuring specific heat capacity. In terms of safety, things get hot, really hot, so you have to make sure you leave things to cool before you handle them and move them around. And I hope you found that helpful, and thank you for sticking around to the end of the video. Please do like and subscribe to Physics with Keith channel so that I can share this with as many people as I can. I'm trying to help people with what little physics I know. I'm trying to help other people out there, giving this away for free. But also don't forget, on Saturdays there is the free online tuition on YouTube Live, and if you subscribe you'll get notified and reminded of that. And you can go to the Facebook page to send me questions in advance if you want to get extra help on a Saturday. And that's open to anybody from GCSE to A-level physics. Stay safe.